Volume, okay. Mic clear. We're like, um, okay. Hello, good morning, everyone. For everyone who woke up early, I have less people than yesterday, but I hope most will start arriving soon, hopefully. Um, my name is Agustin, and this is my third most favorite Monkey Island t-shirt. Okay. First of all, I wanted to ask you about the contest yesterday. Actually, we have the full ranking included Spock, because I don't know the details of how that works, but it seems like it's always like after the contest ends at some random point, the scoreboard starts working, and Spock suddenly is judged within the judge, right? So my impression, just based on the result, was that it was okay difficult yesterday, but as I mentioned, it's not like intentionally increasing or intentionally decreasing or intentionally consisting. It might change. So maybe today it's much easier or much harder. It is a surprise. So do not go to the contest with any expectation. You have to be prepared for both. Very hard and very easy. Easy for final class. It will not be very easy, but it might be easier. Okay. But I wanted to hear if any of you wants to give some feedback on the general difficulty and the kind of problems, like was it okay, or if anything was like, if there's a very bad problem or anything, that's also good to know. Like these kind of problems we shouldn't have. It's nice to hear an opinion. Yes.
I think it would be better if we didn't have CS problems.
Yes.
CS problems.
Oh, okay. Yes, it's in general, there are not that many, like there is no content with half of them, which at some point there was like half from Spot, but I tried to bring two of them whenever I could. Yeah, in general, that is a good point. I tried to select a few that I wanted to mention some concepts specifically, and that might be one reason. Like, I really like this problem, but yeah, I have it into account. Maybe if I can swap. I don't think there are a lot of CSS now remaining. I think that, because I think there were like 4 yesterday, right? So, might be on the high end. Yeah, I keep it in mind in general. Okay. Whenever I can, I might swap for now. Yeah. You mean, I assume that you mean because it's well known, so it's likely to be known, or for some other reason? That's actually, I just assumed you were saying it because of that, but I might as well ask, why do you think it's better to avoid that judge in particular?
Because I think there's a higher chance that many people have already solved.
Right, yeah, that's what I meant. Okay, yeah, understood. Anything else? Any other comments? Was it good or bad? Please, okay, you like to make one. Let's hope it keeps like that. Okay. So today we will have a mix. I was actually gonna lecture a specific topic, but then I swapped the order of the days a little bit, surprised. That's the advantage of never publishing exactly what we're gonna do today. But just to put a title to today's lessons, I would say we will speak about, let's say, more graphs, because we have a few things to complete from yesterday. I might have squeezed a few tricks or whatever since we're speaking about graphs. Plus, general concepts, so it will be a less specific lesson today. But I hope you like it. So I hope you participate a lot. You ask a lot of questions and you participate with your own comments and experiences. And some problem discussion. At least a few of the problems I think are quite interesting, so it might be fitting to mention what their solution, especially if they support the general concept or idea you want to talk about today. Okay. So that will be it. I think we can start now. Any questions? Okay. So first of all, just a little detail to complete. Yesterday we saw the algorithm for, this is a super it's called ICPC. Like the direct minimum spanning tree. Okay? We saw what is called the Edmonds algorithm or the True algorithm or the Bock algorithm, I think too, because they all independently found something really similar. Okay, the generality of the algorithm. Then Tarjan showed how to do it very quickly with binomial heaps and other structures. So there's one detail that we did not end up mentioning yesterday, but I would like to ask you. By the way, there was one, I don't know if to call it easy problem about this, but one problem that quite directly could be solved by just applying the algorithm yesterday. You may have noticed. I think you can use that like to test and see if you understood the algorithm. Then it didn't require any super efficient implementation. Actually, just a correct one, right? That does not have wrong corner cases or anything. But you might as well try just to practice to check if your implementation is correct and efficient and ready. There might be other problems where it is not such direct. So yesterday we mentioned the case where we have a fixed root, right, beforehand. So the first thing we do is we fix the root and our direct spanning tree, our boysense, will have to span from there, right? It's like part of the statement. Which many times is natural, but it might be the case that we don't have a set root, and we would like, okay, the minimum boysense, like from any root that you like I allow you to choose. And I think I very briefly mentioned, like in passing, it should be possible to do that too. Well, the most obvious way would be just run the algorithm n times, right? With every single possible root, so n times whatever the normal complexity of the algorithm is, right? You think we can avoid this and actually use the same algorithm, perhaps with little details in the implementation to not fix the root beforehand? And if so, my question would be, okay, what do I have to do, or what care do I have to have when comparing the I know the root case with the I don't know the root? Could be any node it is allowed.
You should have like a version node, like to every other node, and infinite cost. Run
Like if you have a new node, this will be the new node. These are the originals in a very loose abstract fix. So this will be in very large fixed cost, basically, right? So this will be the same infinity for all of them, right?
Yeah,
all of them will be so infinity is like a huge number, but fixed. In this case, they are all the same infinity. And here we run the algorithm, basically.
Yeah,
Starting from. Okay.
Couldn't you connect with you?
Sorry?
Couldn't you connect with you? Like with a lot of small trees?
We did. It could be a solution, I guess, something like this. Right. You could argue that here you're using two infinite costs. Let's just call it big, right? So it's big, right? B is a very big number. So here you're using 2b plus something which is small and compared to b very small. So any solution that uses just 1b will be better, basically. So if any arborescence in the original without this node exist at all, it will be preferred because you can use that arboricity covering everything and then add one single edge. Right? And we have to add at least one edge. So you can actually use it to detect whether it exists or not. Yeah, I think this works. This is not what I had in mind, but I think that there is no problem with it. I'm trying to double check, but I cannot find any problems. If anyone thinks this is wrong, please tell us. But yes, this seems to work. This is a nice idea and a general pattern. The only disadvantage I would potentially see is you would have to be careful with the infinities that they are large enough, but not so large that we have overflow. So this might be slightly tricky, but in the worst case, this would be like a pair, right? Which is a typical trick for these things to be completely sure. Like, okay, my numbers now are a pair of how many infinities do I have and how many the original number, and you just add them like vectors. So this is like a small implementation of big integer with 2 digits, like another way to think. So these are many common tricks to avoid this kind of. So this might be simpler. I think another way to do this, which I don't know, I haven't read so many times this algorithm to know this is the textbook version of Node because I know like one version that I saw somewhere, but many textbook versions. But basically, we could use the algorithm as is without setting the root at first, because the algorithm, if we remember yesterday's lessons, we actually, like, if we replay and check it in YouTube, we never, almost never used what the root was for any of our proofs. The key proof that if we have a cycle, we can use almost all of it and avoid contractions like all, sorry, I'm contracting to a single node, but removing exactly one edge. All of those key ideas, we never used where was the root, so they work for any root, basically, they are general. So the main algorithm should work. The only detail, the only tricky detail is, I think, to force the root, what we actually did was remove the edges entering the root. And the first step, that is basically what forces that to be the root of the algorithm. I think it's almost like it is running the generic one without root, and by deleting that, it forces that to be the root, because otherwise it will not exist. So if we have no root, we don't do that. The other little detail that we might have is that for the purposes of the calculations of the weights, we said, okay, I will have a new equivalent element, which is simpler and represents the whole cycle. And I know that anytime that an edge is used, here we will be replacing one of the existing edges. So I will, as a baseline, let's say as a reference level, count already the cost of the whole cycle as if I had used all of these edges. So my reference points, so to speak, would be the full cycle with all of those edges already used. And then my weight, so I can add that to the answer, for example. And then the new weights are in reference, how much they change compared to the reference value. That is why we said, okay, using an edge, causes this one to be used, and this one to be removed. So if this one has a weight E, and this one has original weight, the modified weight will be this subtracted by the one that is removed, right? Because that is precisely the difference that is caused when using this edge with the reference point, right? And this works okay because some edge will be used. This node will not become a root. But we knew yesterday if we had some fixed root, because once we removed those edges, that root will never participate in a set. So the only detail, if you don't want to insert a new node, which would be another way to fix it, is that here a node becomes possible, like that in the final solution, in the equivalent modified reduced version where this is just a node, this single node ends up becoming the root, right? And then we would have never changed the reference value, right? So the reference value would, so using it as the root is basically counted as using the full cycle, which of course would be incorrect, right? But this can be fixed by using a different reference value, right? Because this reference value with respect to which we do the difference, right, adjustment, is completely arbitrary. It would have been the empty cycle, right? And then each edge, when used, would have to add the full cycle minus the edge plus the other, right? Anything we put as original reference value, as long as we then compute the difference, would work, right? The idea is that this reference value is what will remain if we never put an edge there, right? So the reference value in this case should be the solution if this ends up being used at the root, right? And which should be the actual solution that we will use if this ends up being used on the root and never receives an incoming edge. And you would need to remove one of these, right? We know that our options are exactly for each edge to remove it. And it was in this kind of superposition where, okay, we delay that decision of choosing which edge to remove to when we put an edge here, because that forces the decision, right? But if it becomes the root, the situation that it never becomes a forced decision, right? So intuitively, we should just remove the largest one, right, to minimize the cost. So we can keep the algorithm as is, and it will work nicely. If we just use as a reference level, not the full cycle, but the best option, basically, the full cycle with the largest and worst edge removed. So this should be, if this is the largest, let's say, largest edge. If we use this as a reference, then it should work automatically. Of course, now, for an edge, its actual weight is the original one, plus the largest edge, let's call it N, because it has to now be included, and this edge E, which it causes to be removed, is removed. And of course, if this happens to be the same, then this is 0 as should be. So we had already chosen correct. So it's basically a small adjustment, and it works as is. Okay. Does it make sense? Which one you prefer at this point might be personal preference. Because this one is elegant in the sense that you use the original, you don't need an extra node and such, but I think it's easy to get confused and forget one adjustment and suddenly you have the wrong number. This one is more uniform. This one might probably be better if you already have the algorithm implemented somewhere as a black box and you want to just call it, then of course this is the usual trick of how to use those things, right? I have my library and it is very static and this is a root, okay, this avoids all the problems without touching the internal code. If I am implementing it myself for the first time as practice or experimentation and such, or I need to do it because I don't have it in my library, I might do this. Any questions regarding this? Apart from not only about this, but any question at all about arborescence before we move on? Okay, good. Let's hope this is like flow networks, you know, that you know about arborescence. You will be able to solve lots and lots of problems about this concept. Again, as I mentioned, there is a pattern that I also see sometimes with flow problems that I say perhaps to some students, oh, this is a flow problem. My students come back with, no, but you never run the flow algorithm. And it's like, yes, that's true, but you can model the whole problem with flow, and then it's just, okay, just running the algorithm will be slow in this particular case, but I know what to do, so how do I do that faster? This can happen with the same idea, like, okay, maybe in this particular graph, the constructions are very obvious for the specific case of that graph, and you think less. Okay. Okay, let's do a quick recap. Actually, because I am probably will be assuming that you know about this, about DFS more or less in general, specifically about the strongly connected component algorithm problem. So who knows DFS here? I would have been surprised if that was not the case. So actually, who I will make a more specific question. Who has read the chapter on Corman et al. Right? Corman, no, New team is one. Right, Corman, Laser, Rivest, and Stein, right? Introduction to Algorithms, CLRS, very well-known book. Okay. Who has read the chapter about DFS in Corman? Oh, this is worrying. Really? Well, a few people only, very few people. So you know DFS, but you can't read about it. Okay. I have to do a more specific question then. We'll have to mention back edges. You sure? I cannot believe this. It's unbelievable. No? That only 2 or 3 people were very timidly raising. You really did not read the DFS chapter in Corman. I mean, you don't need to read the full book. Although I would recommend it as but like it's not so important. But it has 1 or 2 chapters that are very important. If I had to choose only one, it would probably be the DFS chapter. You have to read that chapter from that book. Okay. Can you see this one? I mean, it's darker but very thin, I think. So it might be much worse or better. How readable is this? More, okay, yes. Yes. Hopefully it is more or less. For a while. Forward edges, and there are source addresses. These ones are a little bit less important. Occasionally, it's good to know like the shape of the tree, the forest. But these 2 are essential. Are you familiar with this terminology regarding DFS, or this terminology is also very surprising? Who is familiar with this terminology? Okay. And where did you read about this? That chapter. Okay. Yeah, I have read some of them and they use the terminology, so okay. But you have to go and read the original source. In this particular case, it is very well explained in detail, so I do recommend it. Okay, so this is a recap in the end. Good, that's very good. So basically, I will summarize like the whole chapter. DFS is an excellent algorithm that is not used for mean path. And it's not like typically BFS, for example, as a comparison, is usually used from a single source. That is very common because most of the time we want to do an expanding way from a single source in BFS, right? To compute minimum path, shallowest trees, the ones with less depth. That's basically mean path, right? They are related concepts. All of those things, and usually you do those from a single step. While DFS, you almost always use it in a different way. DFS is an algorithm that gets you valuable valuable structural information about the graph. And this is like, this has no starting node. I think it's useful to think about that difference because sometimes we think of DFS with a start. Sometimes it makes sense, but most of the time you use DFS on the whole graph, and so you keep running DFS if you need to keep exploring the graph. And the reason that you get such valuable information is basically because of this, because DFS will classify your whole graph, and most importantly, all of the edges, will be classified into these kinds of edges, and basically on any graph, DFS will run. Will decompose everything into a DFS forest with many trees, right? If the graph is connected and undirected, it will be a single tree. Right? And all of the edges will be one of these four, right? The terminology is three edges. The ones that make up the trees and the forest back edges go back to an ancestor, right? And you can detect that. That is very important. One of the most important results that you probably know, I assume, is that a graph has a cycle, even in the directed case, especially important. A graph has a cycle if and only if it has some back edge. So in DAGs, right, in directly acyclic graphs, which are a common case, those are exactly the graphs without packages when running DFS. Forward edge is like more powerful three edges, right? They go to a descendant, right? The opposite of back edge, and cross edge are all the others, right? And cross edges, in terms of the drawing, have a nice property. Who can tell me what the nice property of cross edges in terms of the drawing is? Because they are all the others, and like the name suggests, okay, they are the ugly ones. They cross from whatever, something that is not descendant, not ancestor. Right? And they can even cross within the same tree or to a different tree. But there is at least some nice thing about the cross edge. Right, yeah, you guessed correctly. So it depends on how I do the drawing, but if you actually do the drawing in the typical order, like from left to right, as DFS is running, so time goes from left to right, discovery time, for example, at least for each level, right? Because you usually do it like this, but for each level, you start filling from the left. Then cross edges always go to a node that was finished, completely finished before we started, so it's a preview. So if you draw them, cross edges are the ugly random things that we have almost no control, but it can be like that even. But they always go to the left with something head side. So this will be cross, this will be forward, this will be a back edge, and the solid back side. And it's very important to remember that in an undirected graph, you should not have any of this, right? Undirected graphs only have three edges and back edges, which makes everything especially nice for reasoning. There are so many problems that you just think about this DFS drawing and make some deduction. Oh, I cannot get from here to here, but here to that, okay, the edge must be here. Then you just use DFS to do the decomposition, and you will have the solution. Was this very familiar to you, or more or less familiar? Face expression, so mixed. It's a mixed reaction, but with the algorithm itself, you were familiar. Okay, that's great. Okay. Yeah, I think that's enough of DFS. One thing I will emphasize is that an edge by itself has no classification, right? That is ambiguous. Like, before running DFS, it's not like any edge in particular is a tree edge or a back edge, right? It's like in the context of one specific run of DFS, right? This is clear. So if I have the graph and run DFS once, I get one classification. And this combination gives me this drawing, but maybe I do with the same graph another DFS in another order, basically, because that's the only thing left up to choice in the algorithm, which order to listen things when you have it. And it will produce different classifications, right? Just as an obvious example, any edge could be a tree edge. If you have just started there and this is it, okay, it is new, you use it, so any edge can be a tree edge. It's not like this edge is a back edge itself. Once I run it, I have this classification. That's also good too. But anyway, some back edge will appear in any DFS run if and only if there is no set. Okay, so that's these things. That's so useful. And for strongly connected components, it's a very well-known application where the DFS algorithm can be used. There are two main. There are more, but almost everybody uses one of these two algorithms. Right. So the two most known are the Cosaraju algorithm and the Tarjan algorithm, which I guess you have in your notebook or you know them so well that you don't need them at all. So let's do a very quick vote. Who uses the Tarjan algorithm from these two? Okay. Who uses the Cosaraju algorithm? Oh, just as, okay. As a quick recap, this is the one, Cosaraju is the one that does DFS, reverses the graph, and then does another DFS. Okay? And Tarjan is the other. So, again, Cosaraju or Cosaraju. Okay, okay, makes sense. I think, yes, Cosaraju is simpler. If you want to put it in your team notebook, you might want to put Tarjan there because usually it should be like twice as fast. It's more or less like complexities should typically be dominated by the memory and such, and basically this one does two full DFS and two create the graph, and this one does one. Actually, in practice, usually it runs twice as fast. This one does one, this one does two. Very direct. So just because of that, you might want this one. Why use the slow one if you have a faster one, especially for team one? But I agree that this one is much simpler to not do a mistake because the Tarjan one, for strong, it's for the big connected components, there is an extremely similar algorithm, but it's also called Tarjan. And that one I feel is natural and has no really corner cases. But the Tarjan for strongly connected does some very surprising things where it keeps like a stack of pending nodes and a status of whether this is in the stack, and you have like the links of, oh, I have connected to something in the stack, then I would postpone myself to the later one. That is very, very hard to reason about. So my advice would be learn this one, understand it well, and then put this one in your notebook because it runs very fast. But keep in mind that this one is much easier to understand. Any question about that? Okay. So this could be just a very quick recap on this because I want to make sure this is understood. And now you have homework. You have to go and read that chapter. That is very, very important. But you will understand everything better, I am sure. Perhaps a little better if you already understand it well. But you will join the concepts a little better. I am sure it helps. Okay. Then just as a final mention, strongly connected components is a very common algorithm to use as an example of yesterday pattern, right? Yesterday actually we were explicitly using an algorithm that when it found cycles, it contracted them, right? And did those kind of problems very often. Like instead of doing one construction after another, if the graph is fixed, you know it beforehand and no new edges suddenly appear, which might be the case for yesterday problem. You very often can use a strongly connected components algorithm and do the idea of replace all of these for one single element which has the same connectivity. And what will be the advantage of that? Like I have a graph, I do strongly connected algorithm with it, I generate a new graph, and what will I have gained? Right, a graph without cycles, yes, which is a directly acyclic graph. This is such a common pattern that I think it's worth it to just take a moment to write it and fix it in our memory, right, our visual memory. There are many problems that can be solved like this, okay? Like, for many problems, thinking about it in a general graph and thinking in a graph without cycles, right? Which is also a graph which has a topological sort. That is the essence of a directly acyclic graph, basically. It's the same, having no cycles is the same as you can draw it like this and all the arrows go to the right, to the left. It's always to the same side, right? It has this kind of problem. That helps a lot in thinking sometimes. And it depends on each problem. Some problems are basically equally hard, like to think, right, for a human, if they are cycles or if they are not. Like, I want to do BFS. BFS, it's not much easier for a attack. I mean, suddenly you can do dynamic programming perhaps, but it's not like it becomes much easier. But many problems actually are like you cannot do anything if there are cycles and become extremely easy. Well, a few become extremely easy with attack, and others become solvable suddenly, right? And you have ideas. So it is such a common pattern that keep it specially in mind. Okay, but it won't work always. Any question about? Okay. Okay, I have a final graph trick before we probably move to general ideas, but general concepts part, which is even less fun. I anticipated that today's lesson is a bit mixed topic, let's say, so that's hard to put a name. Next, I want to share with you a trick that you might know already, of course. I have seen quite many times. I really like it, but I don't know if it has a name. So I have just invented the extremely original fast BFS or DFS name, right? Because it will be BFS or DFS, but it runs faster than you might expect. So fast BFS, super original name. Okay. So what is this particular trick? It has happened to me more than once, actually, which is already interesting enough, that there is some problem, and I solve it using this trick. I'm like, oh, nice problem. And I then check the tutorial or other internet solution, and they use some much more complicated data structure. So I think there is like a pattern. This is not extremely well known. This is well known. I've talked with many people. Like, this is not a secret, but sometimes people might overcomplicate instead of doing this. That's my impression. So let's go with it. It is basically the same for BFS or DFS. I think I have seen it much more often with BFS, but you could apply it to both. And with similar things, actually, because it might be a more general idea. So what is the code? First of all, what is the complexity of BFS, let's say? We have m nodes and m edges. Right? That's the general setting for anything graph related. We typically think of BFS as taking n plus m time, right? Which you might be thinking, but how can you do faster than this if this is linear time? You have to read the input, right? I see some people nodding, yes, I was thinking exactly that. Well, as you have probably seen in many problems, the graph is not always explicit. It's extremely often that we conceptually create a graph ourselves, like we imagine a graph that is not in the input, let's say. Very commonly, one of the most common examples are arrays, where the input has n things, basically. An array with values, whatever it has, data, but n things, right? And I have a process where I can do things, so suddenly I have a complete graph on those n things, right? But this complete graph is not in the input. It emerges from how I define my connection. So edges appear. So in this particular but quite common case, I have m equal to n squared, so the final complexity is n squared. But input is only n. So now I can hope for optimizing this. Right? And you might use segment trees, you might use crazy things, and there are many problems with many edges. This particular idea stems from, okay, let's look at this complexity and see where it comes from, right? And see if we actually always really need to pay this, or we can avoid it by just being very slightly careful. So I will write the main code of BFS to recall, but in the typical, there is more than one implementation actually. I quite like the one that has two bugs of nodes because it's actually doing the expanding web thing, like the current level and the next level. I don't care if it is stack, queue, what it is. I just need the current level and the next level, so I keep them separate. But the most common is the first in, first out queue implementation. So let's say that queue is our queue, and the typical code of BFS is something like, while the queue is not empty, we have a current node. Let's just say X is popped from the queue. Right? This is very clearly pseudo code, not actual code, right? And then here is a part that probably says something like for y, let's say, let's just write, we can go from x to y, right? So this will be a loop. For each edge that leads to some node y, if not, let's say, visited y, this will be it is visited. We basically visit. Let's keep doing more and more and more pseudo code, right? To visit a node is usually to mark something somewhere and put it in the queue, right? So this is the core of BFS. So this is where the n plus m complexity. Let's see where the complexity comes from, right? Because basically this n stems from visiting every single node, right? While the queue is not empty, we keep going and we keep removing nodes, but the node is only processed once because where we don't visit it or queue it for visiting or anything, if it has been already seen before. So this only happens once for every node, so that's why we have n. So it should be n everywhere, except for this critical part, right? Actually, except for this critical part, because from what I have said, these visiting nodes, popping things, the while, everything amounts to order n in total. Right? You cannot visit a node more than once. So all of this in total is order n. So if we carefully think about it, the part that is proportional to the edges is only this part, counting in total, right? Not per iteration. Do you see it? Because this part will only happen if the node was not visited, so once per node at most. So this visiting thing is only order n. And the same popping and the same everything. Just the checking of neighbors is the only part where order n appears. So if we rewrote our pseudocode to for each y, let's say for each x, y, and visit. This is like the magic pseudocode power, right? I can say things like this. For each unvisited neighbor, do the same, right? I mean, visit it. At the pseudocode level, this seems basically the same, but if we take it very literally, and I mean, it raises the question, okay, when I code it, how do I actually do this? Right? The details are very important here. You can see from the extended version. The most critical part of the complexity is actually there. But if this were somehow implementable, sort of like it says here in a very direct way, okay, go through each unvisited neighbor, right? And you could go directly to each visited neighbor. This would also be order n, right? Because of the same reason. Every node that you visit is new, so it is only visited once in total. So actually, you were right. What is that? EFS is an order n algorithm. This is the complexity when it is implemented, but the good implementation is order n. Unfortunately, sometimes we have no option but to implement it. But in a sense, the skeleton, the key part of the algorithm is linear. So I go through all the nodes once, visiting in this particular order. So if you happen to be able to directly, like, okay, let's go to the unvisited neighbor and go directly to those, the algorithm is linear, right? This is good to notice. Is it clear? Okay, and the thing is that there are quite a good number of problems where you can actually do this quickly, right? There are different ways it could be. You might add some data structure to help you. There might be some property of the problem that allows you to do it. It depends on a case-by-case situation. Often you can have like a set. This is a very common pattern of how to do this a bit faster. You can have a set, right, like as a C++. It's a set of unvisited or pending nodes. So you will take your nodes from there, basically, and that, of course, will depend on how the edges are defined. But so this is just to mention that it is quite common that in order to actually do this fast, you end up using something that makes the complexity actually be L log n, but that can still be much better than quadratic if the implicit graph has many edges. A very common, very common, I've probably seen it like in 3 or 4 different problems. Within this technique, it is quite common. Is when you're not working with a given graph, like you have an explicit graph in the input. Okay, so you will expect n plus m time, and that will be done. But you're not given that in the input. Your imaginary graph, let's say your intended graph, the one with which you are working actually, the one on which you would like to run BFS, is the complement of the input graph, right? So edges are reversed. If the input has that edge, it doesn't count for, right? They want exactly the missing edges to be the allowed. That is usually notated either complement graph or the order graph. Okay. That is a case when you can get the order n complexity, right? Or perhaps n log n, but I think if you use booleans, like a simple array of booleans of such a set, you should probably get order n. Anyway, one of those, either n or n log n, you can avoid the natural quadratic cost, right? Because complementing a graph, even if m is small, in the complement, it will have something like n squared or n squared divided by 2 minus m, which is small, so still it's always huge in general. So it would have a quadratic runtime, but we can use the trick, right? When we do it well, we call everything except this little part. Instead of explicitly going through every neighbor, which would take time proportional to n, basically, almost unavoidably if I actually do it like this, for every neighbor, check if it is not visible. I want to do it like in somehow a direct way. For unvisited nodes, go to them directly. Well, I cannot go completely directly to them on the complement graph because I will have my current nodes. I will have the original edges of the input, which are the ones I do not want to consider, actually, so I will dash them. And I will have all of the others that are the unmentioned ones I want to consider. Okay. So, since I don't want to complement this, what is better to do is to have somewhere a list of unvisited nodes and iterate those. So explicitly iterate the unvisited, right? And I mean all of the unvisited ones, like regardless of X, a global list or set or something, the unvisited pending nodes, and you just iterate through all of them. Right? And the check, you would need them to be neighbors. Right? But you can check that relatively quickly. You just iterate the list, and for every unvisited node, as long as that particular edge is not in the input, you can check. Right? Okay, perhaps that introduces a log factor that will be constant time if it's hash data or something, but regardless, it will be fast. Right? So you check for every unvisited node. If the edge is not in the input, then it is allowed. I go there, and so. What will be the complexity of these parts for a particular node? Well, every time you visit, we can ignore that cost because it will be paid in the total n factor. So the only extra cost above the n factor, n terms, is that we might have to skip some of them. That is an extra cost because we are not visiting anything, but we still have to skip them. But that will only be proportional to the degree of this node in the actual input. Because we only skip things that were mentioned in the input. Like the input actually mentioned the original graph G, which has the edges that we do not want. So those are the ones that can cause skipping. So all of that adds up to M, right? Because for the same reason that the original DFS normal was M. So we go back to M plus M, to the normal DFS compact complexity, but we are actually doing DFS on the compact. Is it? Yeah. Did you know it? Who already knew this trick? Like this is all like, I have done this before. Like this is not new. Okay, some people have, but most, this is new. I'm happy to teach it to you because I like this trick a lot. So I'm very happy that now if a problem appears and this is helpful, you have no excuse. Now you have to know this. Okay? And it is not limited to the complement. Okay? This is just a nice common example. But any situation where you can somehow like process quickly the neighbors and go there, the BFS will naturally speed up. And in my experience, this is often much simpler to understand and code than introducing a lazy segment trio or something like this. There are a few lines of code in the normal BFS plus a set. Like it's not always works, but anytime. Any question? Fast BFS or DFS? Oh, I just mentioned BFS, but you could do the same with DFS and it would be the same analysis, right? It still has a critical part, which is the only source of the nonlinear complexity, which is go through the still unvisited neighbors. It is slightly more subtle because DFS, once it finds one unvisited neighbor, it recursively does things and returns, and then it might be the case that if you have first iterated all the unvisited neighbors at that point and complete them, then when you return they are not unvisited anymore. So you shouldn't do that like here. You should just like be able to, okay, give me one unvisited neighbor quickly. Okay. Are there still any? Okay, here. I recursively go there. Each time I return, I do the same. Right? Okay, give me if there's still some unvisited neighbors, go there. That would be like what DFS does. But you could apply the same pattern. So you can do DFS on the complement because you use the segment. I think this might be used to completely overkill some of yesterday's problem. There was one where you had to like construct a matching or actually a permutation, but those are basically the same as full bipartite matching. And you wanted to avoid like a few edges, so you are like building a matching in the complement of a given graph, which is relatively small. So you might run a very fast matching algorithm on the complement, and I think the critical this will be to slow part is the fact that there are quadratic edges that you might avoid with this trick. But that would probably be overkill, right? I don't think that's the easiest way. But I think it should be doable, right? It might be borderline because I don't think the technique was so generous, but it wouldn't be very far if it's hard to squeeze in there. So that might be a first very interesting possible example. Okay. So I wish you a lot of luck using this idea. Many problems to come. Okay, let's move to some general concepts now, right? This is the more mixed bag of topics part of the lesson. I mean, we're not even centered on graph. Since we are close to coffee break, let's choose a few short recommendations. The first recommendation I have, which I hope you all already do, and Thus, my advice is useless because you're already doing this, but you might not be already doing it, right? Many general concepts like this are prone to writing them like advice or something that you should do, like you should do this, right? So in that sense, we can say the following advice. Before fixing a bug, so I hope a lot of people already say, oh, I think I know what's coming. So let's say you have your code and you're fixing a bug that you found, right? I mean, actually you're not fixing a bug because this says before, so we are before fixing it. That's what it says. I'm getting ahead of myself. So you have found a bug in your code, right? Maybe the bug was already, I mean, you could run your code and it's wrong, right? So you probably had either it was not working on the sample, because you always run the sample before submitting, right? Of course, that's when I don't even have to measure. There are very funny stories about that, but I will skip. Okay. Or you have submitted it, so it passed all samples, but still you're getting any wrong answer, random error, some wrong verdict, right? Some kind of no. So you, for however you did it, you were thinking about it, that it may help you, you randomly illuminated with the idea, you reread the problem and said, oh, I was confused, now I understand. You found a bug, right? But you don't have a test case with you where it fails, still, right? So you are in this situation, you are before fixing the bug, right? So you should do something before fixing the bug. Before fixing a bug, basically get, let's say add, because you probably have some local system of very advanced how to run the test cases, which is usually a file in the test case. Some kind of thing you have where you can add the test cases that you always run, right, all the time in a very simple way, ideally with one key or something like that. So add a failing test case. Okay? And the keyword here is before. This is what is so easy to be tempted. And we have all done it before, like, no, I don't need to add the failing test case. Just do the fix and submit. I think we all have done it. And that's why I can advise it to you, because I have unsuccessfully done that so many times that I can already attest that this is like the right approach. You should, before fixing the bug, because even, I mean, if you're going to fix it and then even before submitting, still adding the failing test case, that combination makes sense. First, create the test. If you are going to do it like that, and then fix it. Especially that way, you don't use the computer, which as a general principle is better to do as much out of the computer to get everything in your mind very clear, and then enter things in the computer. So in my experience, well, first of all, one thing that might happen, something that might happen if you do this, well, how many people do this regularly and be sort of honest? Like if you do it 40% of the time or 30% of the time, that's regular. Okay, that counts. But if you do it once every 20 times, it doesn't count. Raise your hands. How many people do it when you have fixed a few, okay, few confidence. Some were raising their hands, but then doubting, so it's something like this. 5%, if I say 5%, like, okay, more generous. A few more, okay. But most people don't do this. Try to do this. This works. Believe me, you have to do it. I have already tried not doing this, because we all have, and it is better. You get better results. You debug faster, like you avoid it. You get better results. Just trust me on it. Or you can try it for a year, and I will return, I don't know, this market. Okay. So what can happen? First thing that can happen is you add the failing test case, you run it, and it works. That's relatively common. I would, if I had to invent a number, it's like probably 10 to 20% of the time. Or why it's still working? It should fail. So that test case, and it can fail in different ways. Sometimes your test case is, you did not correctly create a test case that manifests the bug, but the bug was there. That sometimes happens. Other times, the bug either does not exist and you're confused, and then some bug exists probably because you got wrong answer or something. But it's not the bug you expected. Or something sometimes you misunderstood how to create the test case completely. Right? So even if that happens, then okay, that is good. That aligns your expectation and gets you a lot of trust that okay, there is a bug because I have this test case and I'm doing it by hand, and it should be yes, and very clearly says no. Okay, I have created a test case that failed. That's awesome. Then you go and fix the bug, right? You add +3 critical place, and that was supposed to fix it. Okay. In my experience, it's about 50-50. Or I don't know, maybe 40, 60, but it's around that. About 50% of the time, the bug does not resolve. And I mean, in this test case, I don't mean with submitting to the system. That is even less likely to fix it. Because problems are hard. But with your test case, the one you made, about half the time, more or less, in my average experience, then the code is still failing. That's the case, and you fix the bug, right? So that's helps in two ways. One, you avoid sending it and getting the wrong answer, which is frustrating and you lose time and has a lot of disadvantage. Apart from the penalty, which is one. The 20 minutes is like the smallest of all of those penalties, I think, in general. But also you gained a test case for extra debugging, for finding more bugs. And that's this is extremely common. So this will speed up. You get used to doing this will actually speed up your debugging process. It's like, I use a metaphor that I don't know why, but there are people that study statistics and some specific, very particular cases have properties like this, but in general it's good. Okay, we don't know why, but it tends to happen in practice. It's as if there was some gravitational pull, and if you have a good test case, which you probably have a good test case, because I told you to think about it. So you had to think about it. What would be a test where this specific thing happens, and then, because for the bug to manifest, I need 3 aligned points and some crazy thing. So you were thinking about it's a nice test case. If it is a good test case for that specific bug, it's like it has powerful gravitational pull and it pulls a lot of bugs, right? This is the mental image. I'm not sure what's going on, but in my experience, this has happened. Like, the problem has 10 samples and 5 random cases that I added. Like, random cases are very small. This is a random test case. This one has no gravitational pull. No bug will ever go to a random test case. Those are very bad. But if you thought of a good test that happens to attract one bug, so you were thinking on one particular bug that you found, and you think a good test for that, and in my experience, like suddenly I had a lot of cases where everything worked, but that test case breaks everything. Like I find 4 more bugs in my code that were more or less unrelated, but this test case breaks everything. Some of you are laughing, which I interpret to mean that has happened to me. I hope if you're laughing for other reason, I will just reinterpret it because I prefer this interpretation. So this is my experience. So that is why, because of this, in practice, this happens. Is why please try it, because you have to practice this, right? If you never practice doing this, and force you like, oh, I just done +1, right? If you don't force you down, we need to practice this because otherwise we will never do it naturally, right? This adding failing test cases, you have to practice this to make it easier for you to be able to do it. You will gain this advantage. You will find bugs more easy. Okay? So this is all from experience, but it is actually. And actually, if all of this did not convince you, I can appeal to authority argument or something like that. And this is basically test-driven development, right? In the very small limited way that like, okay, we're not creating 1,000 unit test and everything, but this is like a little competition specific version of the general concept of test-driven development, like, okay, thinking about the test cases first before writing the code will help me think how I will do the code and what tricky things could happen with the best chance of introducing more bugs. If you notice, that is a general pattern that is recommended, so okay, this is in competition, I think this is, I don't know if the only place where you might want to use test-driven development, but in a specific sense, this is a good place. Any experience that anybody would like to add, or apart from what I mentioned, like from I totally disagree to I also want to add such, because this is such an experience-based area that someone might want to add. There.
Normally, doing the CTD is, it makes writing the code faster because you can test it instantly and instantly see if it works. Instead of having to think like, will it work for this test case, will it work for that test case? Like, if you have
I see. Like you mean, for example, that maybe related to that, it's also good if you can write the code in pieces and start testing it even before it is completely finished, or did I miss it?
No, it's like, it's fast.
That would be another good practice.
It's a faster feedback. Like, instantly you see, like, it did work, it didn't.
Right, okay. Yes, for sure, like the replacement of this would be, I completely finished writing, I think a bit, okay, I think it works, I will submit it. Then later, oh, it was not wrong, not correct. Why? What's going on? Yes, I agree. That's why it will speed up a lot how fast you fix the bug, and I think even more important, how fast you find other bugs. That has been my experience. Okay. Any other comment? Okay. So as you can see, this is a very widely thematically varying class. And similar to this, actually, well, not similar, but related, at least related to this, is another more advanced. This, I think, is very basic. You can have, you're all world final class here, so you are the top of the top, you are very good contestants, but you might have people who are just starting at very beginner level, and this will still be good advice. Like, my A plus B is failing, okay, try to think, okay, it's the same advice, right? It does not depend on this one. If you are a total beginner, but bit too much, but at your level, this should be something to really do and consider. I'm sure some of you are doing it, which is after you have, let's just say, a no verdict, right? A no. Wrong answer, time limit, runtime error, any memory, whatever, any kind of, this code is wrong, but you cannot understand why, let's say. But of course, often you think a bit, read the code, and find, oh, I'm missing this last one. So you realize, oh, this is all completely wrong. Let's throw the problem away, but you realize why it's wrong. Right? So all of those things can happen. But sometimes it's very common. You have wrong verdict, and you cannot understand what's going on, and it should work, it should work, it should work. You read it 20 times and test things, and it should work, but it is not working, unfortunately. Then in that case, an advice or a technique to do is to actually code. So competitive programming is very, very unusual, especially this ICPC code format. It's very unusual compared to live code, because usually coding is hard and you make books. So to solve the problem of I have books in my code, the last thing you want to do is write more code. That only increases worse things. But in competitive programming, you have very short, very specific code, often compared to general code in life, and very good programs. So actually, it ends up being a good idea to write more code in order to fix the So actually code a generator and probably also and a simple, let's say, solution. This could typically be, I don't know, a problem that has, you have to count the number of pairs that satisfy something. So it is extremely easy to write 4 plus 1 and do a simple check, but n is 1 million, so that is too slow, and that's the whole trick of the program, and the program becomes very hard because of that factor. The code would be 3 lines, and you would have a lot of confidence that this is correct if only I could do it correctly. So then to help you in finding the test cases that fail, right, that you need, because in this case you are not able to find it yourself. Sometimes it is very hard, sometimes something is stopping you. You might have like a subtle incorrect assumption that is completely blocking you from discovering that there is a failing test case. Even so, there is, right? So it will be very hard for you to create the test case. Then approach it by brute force. Instead of trying to find a great test case, which very often you do, and then you attract all the bugs and you debug that, start creating a lot of random, like probably bad test cases, but you're generating a lot of them, so at some point you will either hit a good test or have a random lucky test, and find a difference between your code and the brute force solution. Right? So any difference that you found is a bug. One of the two is incorrect. And most of the time they complicate, I mean both can be incorrect, at least. But most of the time they generate the simple 4-4 solution that you trust a lot will be correct, and you will have found some test case to help you debugging, right? So you should try to generate a lot of very small test cases, because that way you can then look at them and use for debugging and understand, right? If that never fails, you might try increasing to at least find a big test case, but okay, that is less helpful, but it sometimes still helps, because you might at least look at it and find value. So this is like a general technique to bootstrap this idea. And this is something that you cannot impromptu do for the first time in a contest, or even a practice contest. Like you have to practice having done this on purpose a few times. To learn how to do a generator and testing and agree with your team, okay, how do we do generator, or do you know some scripting tricks or anything like. You can use the command line diffs, some bash force, and many things. And there are lots of tricks that you can use, but the very basic would be write a C++ code that calls two functions, right? I would always prefer to do it separately so that if some program crash, okay, they are independent programs. That will be my preference, but at the very least, like one single CPP that calls different functions is already helping in this one. My recommendation would be to use it separately. When you can use diff, that is convenient. When you can do bash or force or while in command line, that also helps. I at least use that combination often. But this is quite personal. I know that different teams use lots of different tricks. So you can actually ask for tricks. That might be an interesting issue. So I have an example of this recently. I don't know, maybe a month ago or a bit more. I was participating for fun in a UCAP contest, and I had actually did some casework on paper of a problem, but I had made an error, so that led to later different cases and propagations, so my code was wrong. And I couldn't find it at all, because I was rereading my calculations and obviously rereading them wrong. So I didn't find them there. I ended up doing a brute force generator and a test case appeared. Okay, here it's not working. When I checked it, I finally was able to find, but I was probably looking at it like 20 minutes without the generator, and I could not find where the mistake was, like what's going on, this should work. And then when you have the test case, it's like, okay, perfect. And it was fixable, and with a few details. So that was a happy ending. I finally ended up solving the problem. Probably it took me like an hour and something of work, when it might have worked in 20 minutes if I had been lucky with making that error. but it could have been worse. I could have never found the error. So, from my experience, this helps. But you have to practice. Like you will not create a generator on the fly for the first time. Well, maybe you will, but much less likely. Any question or comment? Are you doing this already? Who has done generator like this before on context, like not after for the web? Okay, so I think about half. Quickly check about half. Okay, that's more than I expected, so that's good. That's great. So the other half, now you know one interesting idea to keep improving. Okay. Any question or comment or idea you want to share? Nobody's sharing their secrets, magical tricks.
Times it takes a lot of time at least in ICPC because the computer time is limited to code like the full
Yes. Yes. That is why, this cannot understand. I mean, you should try to fix it in a different way first. Maybe it's just a +1, and you look at the code with one of your teammates, and you find the +1. And then you work on here. Okay, let's write a test case where this +1 is a problem. But yes, this is like for harder situation. But again, you will face very hard problems, so you will be facing this situation. Right? Because once you solve the problems that you can solve, you will get to the remaining time you need to fight with the problems that you might solve if you're lucky and you're just at your reach. Right? And those ones, it's likely that you don't get it correct and you will need help. Right? But yes, the reflex is not to immediately do this without even checking.
We have a small trick that is sometimes hard to find the answer, but it's easy to generate the test given the answer. So you can write the test case, and after that you just write the answer in the text file, and in your code that tries to solve it, you can read the thing as normal, and after that read the answer and check the end. So you do not like have two codes, have just the generator and your code, but your code reads the answer in the end. Right.
Yeah, that makes sense. Like the generator would be merged with the brute force. It would be a mix where you have the generator and the simple solution mixed, because you cannot separate it. Like because of the way the test case is generated, when you generate it, you know the answer. Maybe because you started from the answer and then flip things and did the case. That is a very common way to know the answer. But not always. Maybe there is a pattern, and the pattern allows you to complete the answer. Yeah, that is it. Also, as a problem setter, there were some contests, like most of the systems where I worked problem setting did not have this feature, but in a few of them, I found a nice feature where you can like do this is the case, this is the generator of the answer, and this is the test case generator can also output the solution, but it's optional. So you have the reference solution and you have the generator that can optionally output the output because it knows because of the way it generates. And occasionally you catch like, oh, the solution is wrong because it doesn't match. Okay. Okay, I think we can go to coffee break. I guess. Be ready. Let's go. So let's get back in 20 minutes. with a little bit of problem discussion. So there are a few that I want to mention. Okay? Actually, I would like to mention about problem, well, I don't remember the letter, but it was something about a game, right? The wins, and the problem circuits, which I think was circuits. I want to at least mention that I find them interesting for very different reasons. So I think most people, most teams, at least in the scoreboard, once Spock returned. Actually, both are Spock problems. When Spock returned, it seems like most people had solved this one. Right? They knew exactly how it was. It had something like this in the name, which made it easy to remember. It was about a two-player game, right? So I think most people solved this one, right? So I am about to spoil it. So sorry, I am spoiling everything. But basically, there are lots of problems in practicing. Basically, this one is like almost a troll problem because always the first player wins. And it is in an unusual form, but this is a very famous game. I don't know if you have read a lot of game theory and you really like game theory, you might have come across the game of Chomp at some point, which is mathematically studied by very smart people, but still unsolved in the full sense. And this is like a specific case, or actually the multidimensional version, and Chomp 2D is already super hard. So if you happen to know Chomp, this is like a sign, oh, this is Chomp. And well, depending how well you know it, you already could solve it. But it might be a sign if you more or less remember it's like, okay, there might be some trick to this one because there should not be like a full general solution. It's unusual. So basically in this one you have many numbers, right? And if I remember correctly, the move was to divide some prime factor from. Sorry, no, to take a number and destroy all of the divisors, right, with it. So you have a list of numbers and you choose one that has still not been destroyed, and you destroy it, and all of it is divisible, right? And a quite common idea actually is, okay, let's think, is to think of primes and factorizations as dimensions, right? So every prime is so positive numbers are factorized in a unique way, right? We know that there's a theorem and everything that any number x is written in a unique way, like this, right? It's prime factorization, and so on. This is very well known. So it is a recurring pattern that this is a way to encode vectors, right? This would be a k-coordinate vector, and the exponents would be the numbers. And so if I need to encode k numbers, I can encode them in the exponents of a number and its factorization. And divisors is like looking at vectors which have smaller coordinates, right? At least for non-negative coordinates, which is the usual, then we keep to integers. We can extend this to negative coordinates even and cover the rationals basically with the same idea, but that's not so common to see, but it might make sense sometimes. So this is a common pattern in, I would say, problem setting. Like you see problems where you can find this pattern of, oh, I can think of primes as dimensions. So that can be useful when thinking problems. Okay. So if I think divisors and dimensions and things like this might help, then you should start with small, simpler cases first, and do specific cases. So the specific case would be single dimension, so power of a prime, or two dimensions, so two primes raised to two letters, right? We could even now call them x and y. Wow, I'm always ahead of myself. Okay, so speaking of dimensions, then we can visualize it like, okay, we have 1, p squared, and so on, and here I have 1, the other prime, q squared, and so on. So each possible number is like it's like a point here in 2D, right? So this problem is something like this, but even in more dimensions because you have any factorization, right? But this could be interesting idea to think of specific cases. So even if I have all the numbers in a rectangle, right? For example, that would be exactly the chomp case. So chomp is this problem played on a rectangle, right? Because with this visualization, the divisors of a number are anything that is on top, on to the left, right, on all this rectangle, right? So the moves can be visualized as removing this, any square that is still not destroyed and destroying that, and anything on above and to the left, right? And whoever cannot play anymore loses, right? I think that was the move. Actually, chomp is the game where you cannot. This is missing, right? Otherwise, it's a trivial first player win because it chooses the big one and deletes the whole rectangle. This is the actual chomp game. The classic, let's say, if you play on a rectangle and n times m rectangle, but it is missing the lower right, so it's a bit more interesting. Who wins? And it is well known that chomp is starting from the rectangle without this corner, right? The slightly mutilated rectangle. So this very particular case, it is well known that it is a first player win, right? So if you happen to know chomp, this is quite similar, and you can get to the answer fast. So this problem is very similar, but we have arbitrary positions, not just the rectangle, and or more general, and especially more dimensions, but the intuition will be identical. So why chomp is a first player win? Because of a general game theory idea, which is the strategy stealing argument. Which is a very nice idea, actually. And it's a rare example when it can be used in competitive programming of some non-constructive solution to problems. Those are not usual in competitive programming. But strategy stealing is a way to know that a game, a position is winning without having a clue how to win, right? But it is a common pattern of the situation. Who knows the strategy stealing argument in general? More or less what I mean. Okay, quite a few, but we might want to write what it means. From the scoreboard, I see that you very clearly understand the basics of game theory, so I won't need to mention it apart from this very quick recap that I'm doing today. That the essential part of two-player games, in turns, combinatorial games of two players, is the most essential idea is the rule that anything that can move to a losing position, which is usually notated with P for previous player, that is the standard notation, it doesn't really matter. In code, this is usually a Boolean. The standard notation, if you read some game theory book or anything, is to use P and N. Because who wins? The previous player, so the one that doesn't play now, or the next player, the one that is playing. I usually remember them as Spanish perdedora and ganadora. That is totally random, right? This is like the official version that you will see in game theory. Okay, so there's this very nice idea that no matter what my other options, they might either not exist, as long as I have one P position as an option, so I can move such that my opponent has a losing position, my position is winning. I am the one who wins. And this is my move. That is essentially the key idea in any game theory problem like this. Okay? How do you win? By moving to a P position. If you cannot, then you lose. The P position are exactly those positions, such that every option is an N position. This is the universal property, this is actually called. In many problems you can find the pattern, and once you find it, if it satisfies these two properties, it is the correct pattern. It's the only way to divide between P and N the positions that will satisfy the other kind of two options, right? And the base case must be correct, right? The terminals must be correctly labeled. In this case, any terminal position should be P because you started, you lost. Okay. what is the strategy stealing argument? It is the general idea that based on this pattern, I know that you know this because there was a problem of subtraction game that was basically do this and almost everybody solved it, so we're on the same page here. There's a general pattern that often happens that you might have, it might not be exactly like this graph, but it's most of the case something very similar to this, and you can do the same reasoning. You have a position such that you have an option, right, that has some options, right, of the game, which you don't really know and don't care and don't want to have to compute. But the situation is such that these are the options of, let's say this is position X and this is position Y. So all of the options of position Y are here. There are no extra options missing, right? So your initial position, if it has more options, even better, you have more options, right? It's better for you. Removing an option for you cannot hurt you. But let's say it has this option to position I, and it also has options to every option of position Y. So that is the key of strategy stealing. This is a situation that is quite particular, but might happen. If your game has this property that you notice at any point, oh, this X position and Y positions have a peculiar situation, it's like Y, like position X includes all the options of Y. So any option from position Y is included in the options of X, and X also includes Y, right? So whenever you have this, you can apply the strategy stealing theorem, which says this is an end position. Here, this is a win. How is the proof? Well, if this position is P, this one wins because you move to the losing position and that's it. If not, this is N, only option. But that means that it is winning, so it has to have a good move, and the good move must lead to a losing position. So there must be some P here, but that is reachable. So this one is N2, end of proof, right? But as you can notice, it has two cases, and we have no clue which case we are. And those we have zero information on where is the good move, but it has to be some, because either it is here, and if not, it has a good move and I steal it. That's where the strategy stealing comes from. If I assume, okay, my opponent has a good move, I will steal it from them. So now I am the one who has the good move. I will do it directly. Okay? It is idea here. Well, this game actually is prone to strategy stealing, right? And the original chomp is in the original chomp, the magic move. So the initial position is X, and Y would be the situation after the player just chops this little part. Then you can see the pattern, the drawing that any move generic like this one has to draw a rectangle that includes this little thing, even the ones on the very borders. But that move was an option and would lead to exactly the same situation from the start. So it matches that drawing, so by strategy stealing the first. And the same happens in this problem. Basically, it has more dimensions because there are more primes, but the analog to do this very little cut is to remove the number 1. It's basically something like that. Because you can notice that any option that you get from the position that you get once you have removed number 1 was a situation at which you could have arrived directly at shortcut without first removing number 1, which is not always the case. Of course, only some games have that shape. Okay. This is here, especially the general idea of how one might apply. As a side note, here we have a very particular chomp position, like the famous one, the starting position, a rectangle with a little cut to make it more interesting, right? This is like the canonical game of chomp. Start here and play, right? And it's funny because we know who wins, but nobody knows the winning strategy. The particular case of n by n is easy because you can cut everything and then you have two identical sticks, and so you just mirror. But the general n times m case is unknown. It's hard. We don't know how to play that optimally, even though we know strategy stealing, let's first play it. And in general, I have, I don't know the proof, but I have read that general positions of chomp, like an n times m rectangles with cuts, so it would be something like like this basically, like a stair, and the interesting little thing there, right? So you can describe this in polynomial size, no n times m, even less probably, n plus m numbers can describe this. So given one of these intermediate positions, who wins is an NP hard problem. That is not number 2. Notice that there are exponentially many states, right? The shapes of this thing that cuts. I'm missing my image. The serruchos, the staircases like this should. There are exponentially many, right? And so that's crazy, and it's a simple example of a game where we actually know who wins by strategy stealing, but we have no clue, and there is very little progress. I think that there is a paper from 2000 something that studies like the initial case of 3 times n. And I think they find a very interesting algorithm that is polynomial for this specific case, and it's something like n cubed or n4. I don't know. So yes, in general, we have no clue how to play this one. Okay. Any question about this one? Especially about strategy stealing? I don't know if you've used it. Some of you knew it, so I assume you had seen it in some similar problem. It appears organically. It's most interesting. This one is a bit short because the answer ends up being, always the first one wins. I think you have to change because it tells you the name of the person. You have a little if. But this is most interesting when it happens like not for the full game and then it's print yes. But when it happens like for intermediate states, so it helps your reasoning at some point, like okay, I'm solving the game and in the middle I say, oh, here my strategy stealing, so you still have a very interesting strategy, but in the middle of that you use some strategy stealing. There are situations like that. And a few times I have ended up finding an explicit strategy, but knowing the strategy stealing idea helped me first to cut paths of solution and finding the explicit how to win fast. Like that can also be an idea. Sometimes say, okay, I know this is winning because of strategy stealing. Now, why is it winning? So it's also useful when thinking. Like you might need to find a move, but if you know that there is a move, or when you are sure that there is a move, can sometimes. Okay, the other problem that I find quite interesting and worth mentioning specifically from yesterday is circuits. This is a quite hard problem, but it doesn't require, it looks like it might need some super advanced algorithm, and it actually does not, but it is quite a tricky one. I don't know if everyone read problem M circuits, but it's easy to state. You have a graph, and you need to add edges to it, right? A simple undirected graph. You want to add as few edges as possible so that every node belongs to a simple cycle, right? And you won't add like repeated edges like this. That will not help the ecosystem. But anyway, forbidden. So that is the question. What is the minimum number of edges to add so that every node, not edge, node belongs to a simple cycle? And it ends up being quite delicate and tricky to think, even though it is superficially similar to some other problems that do not have many corner cases at all. Well, this one is tricky. Okay. Those who are trying to solve it, I don't know if you've thought of cases like this, but these kind of things are easy to miss, like any kind of combination. Because here you have a bridge, and you might think, oh, okay, this will need to be fixed, but you don't need to fix anything because the nodes of the bridge are already covered. Right? So it is easy to notice at some point that bridges are key, because if a node touches any non-bridge, so this is non-bridge, if a node touches any non-bridge edge, then that edge belongs to a cycle, and so the node also belongs to a cycle. So if you identify bridges, candidate nodes that might not belong to any cycle, and those need to be fixed by adding cycles, adding edges, are those that only touch bridge. Right? A single non-bridge touching a node fixes basically. So here, there's nothing to fix. So that is the first idea. Actually, this one has very small n, which is very interesting, like 100. This one can be solved in linear time, because basically you identify bridges. You don't need advanced algorithm. Like a simple DFS and being careful solves this in linear time. But this is very nice that this is done such that, okay, do everything by brute force, like remove every edge to check if it is a bridge, and if you need to check many paths, check many paths. The key thing is find the idea, right? And that's the hard part, finding exactly the idea. So the key idea is first finding the interesting, the candidate nodes that must be solved, right? So they must be nodes that only touch the bridges, but you still have to be careful because, I mean, extending from this example, if you had a chain of things like this, or even more complicated, well, this one you have 3 nodes to fix, right? This one only touches bridges, so they are not in a simple cycle right now. They are the ones in this one are, so let's hide them. But this one is not important. It's like non-critical, because the critical ones are the ones that are leaves, so to speak, if you only look at the nodes that must be fixed. Because this one is in the middle of the other one. So if I fix this, then this one is fixed for free in the middle, right? So these are all hard to know these things, right? There could be any number of leaves, right? There could be another one like this. Okay, here, these 3 would be the leaves, right? So if you have h leaves, you need h divided by 2, ceiling of that, extra edges, because with 1 edge you can at most fix 2 leaves. You can convince yourself. The precise definition of a leaf, you have to be a little careful, but using the fact that n is so small, one very brute force way to do it is like identify the critical nodes that must be fixed. All of them 4 would be like that, and then try paths between every pair of them, so Q is time, like just find any path, and any node that of the critical ones that is found in between 2 of the others, you subtract. Like this cannot be a node and a leaf, right? So it's a quite brute way to avoid corner cases. But you can identify these leaves actually with a single DFS with being careful, very similar to the bridge algorithm. Basically, you need to add the metadata when you process subtrees. Like, okay, I found bridges and anything, and in this whole subtree, if there are any critical node at all, if there are none, it's like this did not exist, right? And by carefully looking at that information, you can at any point know if you are a critical node, and more importantly, if you are a critical node leaf, so to speak, right? Basically, you need to have one and only one edge that leads to a subtree that has some other critical node, right? These ones that have no critical nodes could be removed for our purpose. But this is still not the solution because this assumes that everything is connected and nice. Right? Basically, you will have to add this over every connected component because you cannot help it like connected components work sort of independently. And then we have to be careful of single nodes and connected components of 2 nodes. Right? This one is more or less, let's say this one is more or less normal because it has 2 critical nodes, right? So you would count it as 2 leaves. But this one you will have to be careful with this one and count it as 2 critical leaves too, right? Even though it looks like only 1, because if you count it as only 1, you might end up. Well, for the purposes of this, it is the same. Maybe it's okay to just say this is 1, but I find it more natural to think, okay, this is exactly the same as this. I still need to connect this from 2 different places.
Like this wouldn't solve the situation. But this is this small graphs involve a sort of corner case. Because basically, okay, any of this that appears will add 1 to the answer. Right? Based on this calculation. Right? But actually, that assumes that you can do this. Right? Which you cannot. But as long as there is anything to fix anywhere else, like this, which also requires 2, well, this will count as 2 divided by 2, only 1, right? Would be correct. Well, I can merge this in between, right? And actually go from here to here and from here to here. And so I can solve it with only 1. It's only that the one that I have to use is like extended, in a sense. Right? So the correct calculation is still h divided by 2, right? It's only that if there is nothing where I can hang my nodes, I end up having to pay an extra +1, right? Because I need to go and do this extra hanging because I cannot do multi-edge, even though the other parts were solved, right? So it is tricky, but basically you count everything that needs to be fixed, and if there are very few things, like less than 3, basically 2 nodes to be fixed only, or 1 node to be fixed only, in that case you don't have enough to do the hanging, and you have to do +1. So that is basically either the only thing that is broken is an isolated node, or the only thing that is broken is 2 isolated nodes, or the only thing that is broken is a component of 2. Those are the cases where you end up needing the +1. Right? Any other case, this calculation still works because you end up like saving the day. For example, if you have these 2, you would say, okay, this one needs 1 and this one needs 1 by itself, right? Well, they can be linked together happily, so you solve it, right? But this one, if all of the rest of the graph is correct, you would think 1 edge is enough. Well, no, you need to solve it because you have nothing to piggyback and attach for free. Right? So it's very easy to miss any of these cases, but no heavy algorithm is actually like used anywhere. It's not like let's learn a very new algorithm, right? Be careful of this. And these are the 3 most critical cases where you basically have to do +1. It's not that the full graph is less than 3 nodes, right? Or very little. It's just that the part that has to be fixed is very small. Right? I don't know if you thought a lot about this problem, but now you can try to implement it. At least I think it is very educating. Instruction.
Question.
Yes.
In this problem, if you had the case, if you have a triangle, and
Yes.
you have a path of vertices to another triangle,
Separate.
yeah. Like, choose one vertex.
Do you want to come and draw it? If it's complicated, it might be easier to. It's for me. Nice. Right. So, first of all, the criticals would be, is it not critical because it touches non-bridge things. So I think only these are the bridges, only these end up touching only bridges. So these are the critical ones. Yes, and there is some connection here, so only these 2 should be the edges. The leaves, right? For example, by the very brute n-cube approach, I would take every super technology. Every pair of these critical nodes, like this with this with this with this, I will select m squared, and then for each of those, do another, well, that would be n squared times m, but m is 1000, so I think you can play all of that, very brutal approach. For each pair, find a path from this one to that one. Well, if you do single path, it's probably a single n squared. Anyway, you can do that very good, find a lot of paths, and anytime you find a path from here to another leaf, that path is through a third one in between, you can discard the in-between one, as that one is not a leaf. And that brute approach will filter everything here except these 2 points. But you could be doing one single DFS, and no matter where you put the root, if you are careful when you do the bridge calculations, like let's say the root is around here. When you are here, you will say, at this point, you will see, oh, this edge this subtree does not contain any critical thing, so it's as if it did not exist, but there is a, but this one is a bridge, so you know that you are critical. That part is the easiest one. I think it's just identifying bridge at that very same moment. So here you could know that you must be a leaf critical node, because from all your neighbors, which in this case are only 2, there is exactly one of those that will contain another critical node possible. Right? If there are 2 or more, you are not a leaf. You can detect that, but you have to be careful. Like the final code seems very, very short and nice because it's the normal DFS of bridges with a little checks, but you have to be very careful with those checks. Okay? And this general corner case. Okay. Any question? This one was used in a very old Argentine tournament. Argentine programming contest. That is the translation. Argentina de programación. And nobody solved it. But a lot of teams were trying and very close because of it has many tricky cases, which is surprising because the main statement is so natural. The tricky cases, the tricky corner cases naturally arise. Right? They are not like put there on purpose. Okay. Yeah, I really want to go back to this idea that we already mentioned yesterday, right? Of this very important concept. Speaking of problem discussion, right? Within the general framework of the direct spanning tree algorithm that we saw yesterday, the Arborescence Liu Edmonds Bock algorithm, we saw this general pattern of an idea to replace things, right? To do replacement of, we were saying many things. It doesn't necessarily need to be many, but they have to be more complicated. And usually having many things is more complicated than having less things. Replace many things by simpler equivalent things. So those are the 2 keywords, right? Make a replacement to get to simpler things so that we are doing an improvement, actually, and not making things more complicated, of an equivalent element, equivalent thing. Okay? Of course, if we replace something, we do not want to destroy the solution. So this is, of course, a very general pattern, and you can apply it to solve many problems. I think one of yesterday's problem was, I actually had first found that problem or idea in I think it was the Havana Online Judge or something, but I don't remember the correct name. I think it's not named Havana. It had another name and I cannot remember. But it stuck with me because it was a very nice idea. And then I think I found it in some other judge and so But this appears in a lot of problems. I don't know if someone has any example, maybe a well-known idea in this pattern. Like I don't have one single one in mind because this is so common. But perhaps I think we mentioned like collapsing strongly connected components into one single node to simplify and even remove all cycles was one example of this general idea. Right? There is one well-known trick regarding this that is used for knapsack problems sometimes, or for subset sum, right, which are extremely related, those two ideas. I'm not too used to doing it that way because I usually do a different trick. But there is a nice trick about this to avoid repeated elements. Like if you have something similar to subset sum and you have many copies of number 10, let's say. Well, you can actually try to reduce the total number of elements to make your life easier and your code more efficient by noticing that if you have many copies of the same element, you can, for the purposes of subset sum and many related knapsack versions, like not all of them, some related knapsack versions, you can do simplification and replace many things by similar equivalent things in this case. An idea how we might do that, actually. I think the simplest case is to just take triple repetition. If something is repeated 3 times, you can notice that you can fuse 2 of them together, right? So this one right now I'm sort of ignoring. And these 2 things behave the same. And I think this one is simpler because it has 1 less number. Right? Why do they behave the same? Well, what numbers can I create with these 3 terms? Well, very clearly 0, 10, 20, and 30. And what numbers can I create with these 20 and 10? Well, by checking the options, it's 0, 10, 20, and 30, which are the same for options X. So the options of what I can create are exactly the same. So if that is all that I care about, you can do this with placement. And so you can get, by just applying the rule in this, which is very simple in this particular case, you can actually get to a situation where each element appears at most twice, which can be helpful sometimes, right? There is a very common pattern or trick that when you have things that you know that add up to a certain number, let's call it S, if those things are different, I mean they have to be integers, right? They are positive integers and they are all different among themselves, then K is at most square root of X, right? This is a very well-known trick. You all knew this trick already? I think most people are nodding, others are not, but maybe they know it too. This is very common, so it shows why it might be helpful sometimes to do a simplification of avoiding duplicates, because sometimes when especially when this happens, the total sum is fixed, which is natural in this kind of context. Making sure there is no repetition ensures, okay, there are few things, asymptotically few things. So it reduced maybe S copies of the number 1 to only square root total, so it's a big improvement. With this technique, we will get 2 copies of everything, but still it's order square root, like how times 2 factor, right? So this technique would be enough to reduce the number of elements. Right? But compared to other techniques that can take advantage of this idea of processing all the general pattern will be processing all the duplicate elements together, right, somehow, so that there are a few categories, let's say, of elements. This simple idea might many times be easier to implement, but it cannot do anything, right, because it did not change the numbers that I can create, but it did change something else that might matter many times. What do you think this transformation did change? So regarding what numbers we can create, this is equivalent. regarding something else related, it is not equivalent. What do you think is? There might be more than one thing, but one important example of something that is not equivalent when we do this transformation.
Number of solutions.
Yes, you're all in agreement. I agree with that. That's what I had in mind. The number of solutions changes significantly, right? I mean, if you want to count, it might depend on how you count them, but the more typical way to count them would be, okay, these are distinguishable elements, and so a solution to me would be a big math, basically. Which items I did choose and which ones I did not choose, okay? And that changes. For example, to create 20, I have 3 ways up here, but I have only one way. So I have transformed. And it's not a fixed transformation like for any number I have divided everything by 2, right? Because then if it is a control transformation, you can very often fix it. But here it depends, right? It's not like a constant factor always the same. It depends on what number I am creating. So yes, that is something to take. So this is a well-known example of this general. There are many more. This is a common pattern, so it's good to explicitly keep it in mind, right? Okay. Regarding this replacement pattern, one example of that could be yesterday problem, which is, it's called mean cost pairs. So regarding a bit going back to the question of try to avoid CSCS a little bit, I sort of agree, but basically I wanted to explain it. Since I really wanted to explain it, then I'm sorry, I included it in the content. I think it's nice to have it and then explain for this particular case. So this problem, actually, I mean, I knew already when I thought about this problem a related problem, so I basically did a reduction of this problem to the one I already knew. And the one I already knew, I applied this idea, right? So I think it is a great example of this idea. In this problem, I don't know how many people have solved this problem. Who has solved this problem at some point? Okay, but I don't remember the, was it I? L? Okay, this is L, it seems. Okay, so some, but many did not. It is not an easy problem by any means. I think I could solve it quickly because I basically already knew by memory a very related problem. Otherwise, I think it's not easy at all. But it is nice to practice implementing, I think. So let's see how one can solve it and how it relates to it. Well, first of all, I do not have it explicitly listed here, but a very fundamental concept that you surely already intuitively know is that if the input represents something that does not have a well-defined order, then I should sort it, right? And that's not always the case, but you can, right? Permuting the input does not change the result, then you are allowed to sort it, then why not sort it? It might help, right? And it's surprisingly often very useful. So here sorting the cost of the pairs helps a lot. So basically you can imagine that we will have a sorted list of, I don't remember, they could be points on the plane, these numbers, because the important thing will be the distance, right? So I want to make pairs, and the cost of each pair is just the difference. So this one costs 10, and this one costs 7, and so on. And I want minimum cost pairs, right, in total. The total I want to be minimum, not the maximum, let's say. Those will be different things. The total sum I want to be maximum. I want to control k, the total number of pairs. And basically not only control it, they ask all of the possibilities, right? I want to know for k equals 1, if I make one pair, what is the minimum cost? If I make 2 pairs, what is the minimum cost? And so on. Pairs have to be disjoint, right? They cannot touch, of course. So this is the problem setting, and this goes up to the maximum possible, which is around n divided by 2. Okay. So first, two geometrical, very common observations actually. A drawing like this, where my pairs cross, makes no sense. Because by the very powerful argument of drawing the cost on the board, I can see that I am paying all of this cost if I imagine this as actually points on the plane. So this is at location 8, and this is at location 20. So this horizontal bar from 8 to 20, well, it's horizontal with an arc, but it's imagine it is horizontal and flattened. This is what I am paying. So you can see that this this one went up to 15, sorry, otherwise I am repeating. Okay. So we see that this in between distance is actually like duplicated. I am paying it for it twice. So I have a very simple exchange argument that I can match this other way and I pay less. I have basically reduced by twice the intermediate. And this is a very common pattern. I would guess you very likely have used almost this exact drawing argument at some other problem. If not, keep this drawing in mind. It is a very common situation. So first observation, my pairs will never cross. And once you know that your pairs will never cross, well, you will have pairs like this. And then the second simpler observation is, okay, if you have pairs that do not cross, even more, you would like them to be consecutive values, right? I don't know, 10 and 12, let's say, are consecutive on the list. That is what I want. I would never want to skip, right? And that is even easier to notice, right? If you use shorter lines and you are reducing the total length. Nothing to say. So that is the situation now. So we want to use consecutive pairs, right? And each pair has to pay the difference, right? So that is how it reduces to another known problem that I had seen before. Once you do this, you notice, oh, then I am only paying for some difference among consecutive values. That is the end thing that I will use. So this difference is 5. This difference is 2. Now this is not sorted anymore. Right? No, this should be 5. This one, let's say, is 5. Assuming this is 15. And this one is 8. What let's say. So now I can basically forget about the original numbers because these consecutive differences are all I really need to care about, because I know that I will be choosing some of those consecutive pairs. I need to choose k equal 1 of this, k equal 2 of this. So in terms of the blue numbers, the rule is that I cannot, it is easy to see that the rule is that I cannot choose 2 adjacent elements. Right? As long as I choose k elements in this blue part that are not adjacent in this, like a new array, like this. This is my new array, just the difference. I want to choose 1 number, 2 numbers, 3 numbers for the maximum sum without having to consecutive. Right? Everybody sees that this is the same. Okay, and that is the problem that I already knew, so that's how I solve this one quickly. So this is another example of a very common pattern that is reducing one problem to the other. I will mention it in a second. Another way to use that idea. Okay, so what do we do now? Here is the part that if we look very, very strongly, right, at this array and think about this problem a lot, we might arrive at the idea. Well, we might want to build. First, sometimes one does not know what to do and start trying different techniques, right? One technique that one might try is, okay, let's try some greedy algorithm or something like that and see if it goes and works well. Here it will end up working, so it will be some kind of greedy algorithm. But one tip that might give some intuition that perhaps we need something greedy is that the most classical way to solve this, I think, would be dynamic programming. Like, let's say we did not have this. This is similar to the lambda optimization class by Andrew, but we will not use that optimization. But it is a similar setting. Like, we have some problem that we can efficiently solve with dynamic programming, but we have a restriction. But that we have to respect of how many of something we use. Here is how many elements, basically. If there was no restriction and we just want maximum sum without 2 consecutive, that would be a very simple dynamic programming algorithm, right? For each element, I use it or I don't use it. I can use the recursion to the previous. I assume you all know that. But here we have this constraint. So the most natural thing to do is to adjust that recursive algorithm and add one parameter. I have n elements, let's say, the first n or the last n or something like that. And I want to use exactly, or I have used exactly up to now, there are many variations, k intervals, right? So your transitions are basically the same, but you either leave k as it is if you did not select an element, or you reduce or increase depending on you're doing it if you use them, right? But this, of course, this would give a very simple, natural, correct algorithm for this final part, and we would get the full table for all our k values if we solve the problem. But we need to do something better because of complexity. This would, of course, be n times the maximum k, which is n divided by 2, so this is a quadratic algorithm. So only complexity is in our way, right? And we might try one of Andrew's super powerful optimizations here, but I cannot think of one that works because here is like a tip that we might have about this problem. Maybe there is some way to solve it with some kind of different, crazy optimization that is very different to what I am going to do, but I don't know of any. I saw the code of some teams, and I think they are doing a more complicated version of exactly the same thing, and others are doing exactly the same thing. So I did not find a radically new idea. But there might be, I don't know. A telltale that, okay, this might need something else, like really something more magical that relates everything together, is the fact that we need all of the values, like not only one. We need only one, perhaps there is some optimization trick that like lambda optimization, and we can aim for our desired k, perhaps. I'm not sure, it seems like it should work, but I won't even think of it because I am not aiming at one single k. I need all of them. So I need to do something. And there are this situation where you need all of them might make you think, okay, I want to build them incrementally, right? One at a time, increase by one element at a time. That might be a way to have intuition to quickly say, okay, let's try something real. But otherwise, you might be forced. Maybe this is dynamic programming, maybe this is greedy, maybe this is graph, and start thinking properties of the problem. In this case, a very the key properties that this problem has that will allow this replacement, it can be noticed when you think about the smallest one, or the minimum element, basically. Right? Let's say, first, for a simpler case, let's pretend that the smallest element is actually, we want minimum cost, right? If we want maximum, it's exactly the same, but let's pretend for a moment that the minimum element happens to be by chance on a corner, right on one extreme of the array, either at the beginning or at the end. Is there any reason ever to not choose it? In a solution, either for k equals 1, for k equals 2, for k equals 3, we will need to choose one element, two elements, three elements with a restriction that we don't choose two consecutive ones. That is our problem. For each and all of these k values, is there any situation ever where we would not want to choose this first element if it happens to be the smallest? Well, if we think about it a lot, I think, it might be if we extend, this might be useful later for thinking about the algorithm. If we had the k equals 0 case, okay, we would have to say, well, for k equals 0, we cannot, obviously. And this one has the answer 0. But other than that, as long as I choose at least one element, I will always have an optimal solution that uses this first element, right? Basically, by a simple replace argument, choose an optimal solution. If it is using this one, great. If not, consider the first one of those elements. For example, it might be this one, and just pull it back here, so to the first one. It will reduce the cost because this is the smallest one, and it will not create any collision because this one was the first one. Right? So that already hints at some greedy structure. Oh, okay, the minimum is that corner, you always have to use it. So that if that happens, we can solve the k equals 1 case, right? But we then will need to continue solving other cases, right? So let's for now pretend that it did happen. The first element is the smallest one, right? This is the smallest element. So for k equals 1, I will use it. So the solution for k equals 1 is this element. I already store it, write that cost, or print it even. I think this prints everything in order. So what can we do from now moving forward? Now we would like to apply this idea of replacing things by simpler equivalent things. What is the situation? We will now have selected this element, but we might need or want to change that later, right? But luckily, in this case, we can repeat the same argument for any k, and like we said before, we can pull back, so we will never need to not use this element, right? So the equivalent situation for the future is that we will never be able to choose this 5, right? Because we know that any future solution will use this one, and thus it will not use this one. But from this point on, everything is free, right? So actually, this is like the happy case, the easy case comparatively. If the minimum is at one endpoint, we can actually say that is the solution for k equals 1, and that will be part of every solution, so we chop. This does not exist anymore to our eyes, and we move to a problem where we have already chosen 1, so now when I find a solution for k equals 1, it will actually be the k equals 2 of the initial, the 2 will be the 3, and so I can keep going. So I have reduced the problem to an equivalent, simpler problem. We would like to do the same even if the minimum value is in the middle. And that is the key idea to solve it. Let's say the minimum value happens to be somewhere in the middle, like here. Right? There are elements to the side now, at least one at each side. And they are bigger, so I don't know. 1, 3, let's say, anything bigger would do. So now, for k equals 1, obviously the solution is still take the minimum. So that part does not change. But now we have to think very carefully what is the equivalent situation for the future. Right? Because now it might make sense to, for example, for k equals 2, maybe it is a good idea to stop using this. Or perhaps for k equals 10, at some point it might become a good idea to stop using this thing. Right? We cannot do a simple argument like before that we will always use it. I mean, if the whole array was with 3 elements, for k equals 2, you would need to actually split it into 2 and 3 because you cannot use 1, otherwise you don't have room to put 2 elements, right? So that would be one example. But what are our other options? What are our options? Like one option is of course to use it. And then we will proceed as before. We use this one, we cannot use this one, we cannot use this one. And then we need a solution of the rest where we do whatever we want, right? But if we do not use the minimum value for a future solution, then we can think, why would that be the case? Why would we ever want to not use this minimum value in the solution? Or a similar way, like thinking in the opposite, when could I use a replacement argument to say, no, you should definitely use the first one, right? Let's look at the neighbors, right? Because I haven't drawn anything else because it's too far away. So let's look at the closest elements, right? If the solution in the future does not use any of these two neighbors, then of course I could do replacement argument. There must be something used somewhere else, I swap it, no collision, and it works. So if I ever want to not use it, it must be because I want to use one of the neighbors. But if I use only one of the neighbors in the solution, Well, it's similar to the exchange before. The neighbor is not better than I, and I am not using the other one, so if I just swap and say use this one instead and stop using this one, no collision and we improve. So we discovered that the only reason to ever stop using this element in a solution, otherwise without loss of generality we can do the movement. The only reason why we might want and need, prefer, strictly prefer, like to not choose it, is because we want to choose the two neighbors, right? Like this is obviously much worse for total cost, but here we are choosing only one element and here we are choosing two, so it is a different situation, right? We cannot directly compare. If this were all the elements that we have, like we need to do this for k, right? So this might make sense. So these are the only two options. That is the result of our analysis. As long as we have k, for k equals 0, we know that the answer is 0 and we cannot choose any element at all. But for any k at least 1, our casework shows that, okay, we will either choose the minimum and k minus 1 other things somewhere, or then in order for this to make sense, k will have to be at least 2, right? But the other option is to choose the two neighbors of the minimum, not the minimum, and then k minus 2 things somewhere. Those are the only two options. Okay? Is that clear? Like the case? And this leads to the idea of replacing but by an equivalent element, right? Because in this case, the upper one, it will be okay to use this element, no collision. But in the lower one, for those same 3 consecutive elements, it would not be okay to use this one because it will create a collision. So, if I had a magic device like this to hide this, I told you to guess what is inside this secret box, right? This is high technology display. What is like this? What is inside the hidden box? Well, you might guess that there is a single element, like not 3. You might guess, okay, here is like I did not choose the element and I can put anything in the neighborhood, but here I choose the element, so I cannot use the neighbor. This looks like from the outside, if I ignore the details, this looks like a single element. That is the idea. I can actually do a replacement by of these 3 elements, the neighbor, the minimum, the 2 consecutive the 2 neighbors of the minimum, by a single equivalent element, right? Because if I do not choose this element, well, I will have 0 cost, right? But if I do choose it, let's say this one has a value of W. If I do choose it, well, I will have a cost of W, right? While in the original, we can compare. And the effect on the outside is identical, right? Here I would not choose it, so 0 cost, I can do whatever with the name. I do choose it, okay, W cost. Also, it is important how many elements I am choosing. Here I am choosing 0 elements, while here I am choosing 1 element. This will affect the total number of elements, right? While here I am choosing 1 element, and here I am choosing 2 elements. Okay. Right, we're starting to see a lot of similarities. That's precisely the point. Here, how much would they pay? The cost would be only the element, only the minimum element. Let's just use the numbers in this example. It's the same each time. And here, I would pay, let's say this is the cost. And here the cost would be the sum of the neighbors. Yes, the sum of the neighbors. Yes. 2 plus 2. Okay? So this is looking very similar, but it's like it is shifted, right? So there is like some difference in cost from choosing and not choosing, right? The numbers are like not equivalent because for a single element, it will always be 0, the cost of not choosing. Here it's like there is a fixed cost and it gets modified if I do choose the element. And it's also shifted like how many elements I have. Here it's like, okay, I have already chosen one element at some previous point, which is the hidden minimum inside, and I can choose one more. Here it's like I have forgotten because I don't have the details, but still the important thing is I have the option of choosing one more element for some change in the cost. In that way it behaves identically. So it's just a matter of taking the difference. We can replace it by a single element of actual cost is difference, right? The sum of the neighbors minus the minimum element. This is in general the calculation that we will do. Right? And from now on, choosing it will add, have a net effect of adding one element. In that way, it behaves like an element. The detail is that internally it just changes 1 into 2, but has the same net effect. It adds one element to the solution, and choosing it does some shifting, it adds some constant to the current value. So we have to know that the current value is 1. We basically keep adding the values for every choice that we do. This 1 would already be in the solution added. And this always is like the delta, the difference from the previous solution for some k to the k plus 1. But we can see by just all local considerations that this replacement is correct basically. This new fake element has identical consequences for all the outside observers than a single one equivalent would have. Right? Is that clear? So I hope you see that this is a particular very nice example of this very general pattern that we see come up a lot. This is quite involved. The idea is nice. Once you see it, it makes sense, but it's not so easy to see. And do you see that this, if efficiently implemented, could be directed to an n log n algorithm, right? The whole problem. Because we can efficiently implement this pattern. There are different ways of how to do it. Basically, at every step, we need to know the minimum of the current existing values. We can do that with priority queue in logarithm time. Then we have to, once we find it, do this surgery on the array and modify our values, right? Basically, we will have to add a new value to the priority queue, so we need to know the neighbors. The critical part is that we will need to know the current neighbors of this node. So we need to find the minimum node, know its index, know who are the neighbors, and be able to do this cutting and modification, right? This can all be implemented with a single priority queue and a homemade linked list. Yes, someone said list, linked list. You can use even C++ list, but I think it's harder. It's easier to have like the left and the left of I and right of I pointers. Well, this could be indices, and you actually have a linked list of the living elements, right? So that way, instead of deleting and shifting everything into an array, you can actually, when you do the transformation, delete the neighbors in the linked list, because you are doing the local modification, you know it, and the new element just change the value here, right? So your priority queue should have the values, but also the index, so that when you pop the minimum, the current minimum, you know where it is and you can do the modification. This leads to a very efficient implementation, which might be tricky just because in-place modification of anything is tricky. And that is a general pattern. So a less error-prone version is probably to use a set of indices, of alive indices, so that you can do ladder at the time and erase things. And inside, of course, all the careful manipulation will be done, but set as it's coded already, right? And that will have much worse constant factor, but it works, right? And I have coded this one, and this too short, nice code, but I made a few bugs in the process. So I believe it is more error prone. So you might try the set, and if you then need to optimize it, you can change it to this, because the main code ends up being correct. Okay, and that, of course, incrementally, when we look at the full algorithm, it incrementally starts producing these values one by one. At every step, the minimum tells you how much to add. Any question? Yes.
you do the replacement, you should erase from the priority queue the two elements of the sites and not the new one.
That is a good question. That's up to implementation. Usually, because C++ gives us a priority queue where it's not convenient to delete, what I did was I do not delete anything, but I have an array, or I already had this value, so I also have an array of booleans that says if an element is alive or has ever been erased, and if I remove from the priority queue something that has been erased, I skip it. Similar to the trick that is using die strategy to skip all wasted entries that are not fresh anymore. Okay, but you could, like, if you had control of that heap to make everything tidy and use perhaps less memory, you could delete it yourself. But probably it's easier to just keep them there, but be able to skip them when you take the minimum. Oh, this one is old entry, and keep them.
Okay, and merging the borders in the element you are erasing guarantees you that in the priority queue you don't have an invalid element. I'm not phrasing that correctly.
I think if you do it as I mentioned, at any point, anything that you remove from the priority queue that says here that it has ever been deleted, it should be skipped. Anything that, and the reverse, so it works. Right. If you create a new place for the new element and don't put it in place here, like it becomes tricky because where is it, right? So that is a very nice thing of doing it like this, like erasing the neighbors, but leaving that one changed. Because also that is the entry that you have just removed from the priority queue. So it's like you remove and now you put a new equivalent one, and these two remain, but you mark them so that you can skip them.
That's what I was
That
trying to
makes
say.
sense.
Thank you.
Yeah, and there are many ways to implement this. I think this will probably be the cleanest idea of implementation. But I saw people using what looks like some lazy segment repropagation range update of alternating intervals of signs things, which if you look carefully is the way it would behave like a multiple merge. If you start merging many of these in chain, and you look at what would be the super merged node, right, and you try to interpret it in the original, right, it would behave like something like, okay, I can flip the signs of all of this, like plus minus, plus minus, plus minus, and flip the whole. But it is much easier to reason in terms of a single merge, right, and not what happens if I do multiple merges in a row and interpret that in the original. So in that way, I think those are equivalent versions of this. I think doing replacements one by one is cleaner, but that's also a big subject. Like I would, to me, it's not natural to arrive at that idea without doing this first, but I can imagine thinking of those ideas first. That's also an option. Yes?
In some cases, it might happen that you will need to use an element again. Like, you start with the minimum, and then you might swap it for its neighbors, right?
Well, yes, in a sense, that element, I mean, as far as this analysis goes, the original element does not exist anymore now. We have transformed it, right? And we have the new element, right? But yes, in terms of the original one, now you put something in place that if you once again choose it, it once again uses that element.
How do you make it? How do you make this? How do you model this? You model.
Well, I actually don't. I am just adding cost. Perhaps you mean how do you reconstruct the solution, the full detailed solution from this? Because the answer is then, that is a bit tricky. And luckily, if we only need the number, we can basically forget about the values that we are replacing and just do the replacement. We can recover everything, but we have to keep like pointers to the previous place so that at the end I can recall back and say, oh, okay, this element actually was this and this was this, and I built a solution. Or some other equivalent way, right? But it's much nicer if I don't care about it.
Without, I mean, if you have like this, in this case you have the 1, the 2, and the 3. Right? It might happen that at the first moment it is better to swap the 1 by using its neighbors, right? And then later it might make sense to swap the neighbors for the 1 again.
Okay, let's do a short show here. So we have the current minimum at this precise step and its neighbors. And so I do a replacement, and now this becomes a single element, which is x plus y minus m. Okay, and later I could choose this one again.
Yes, I mean, you can choose the minimum again.
When I do, well, later it will have another two neighbors, z and, well, it could be on the border, right? When it is on one extreme, it's like it's never considered again, because we already said that if the minimum happens to be on the border at any step, we don't reintroduce it. We just say, oh, I will choose this one, I will not choose the neighbor, that's it. I remove them forever, that's a fixed choice. It's the easy case. That's it. But if it's in the middle, it will have new neighbors, I don't know, W and Z. So it will get merged again. If we look at the original value, so the merged value will be W minus X plus M. So it's like it is coming back again, minus Y plus Z. Right? This is what I mean by multiple merges end up working like plus minus, but we don't need to care about that. So merges all the way down. Does it make it clear, or is there further question?
Yes.
Okay, so it's not like we are never considering putting that element again. It's just that it's becoming explicit. Our analysis, the old element does not exist anymore. We now have a new equivalent element that is equivalent to the full situation, right? So the equivalence has its details, right? That's why reconstructing is slightly trickier, but it's basically like running this process backwards. Every time I do a merge, I could store somewhere something like said, oh, okay, this node actually was in the beginning 3 blocks, and then these 3 blocks say, oh, when I was merged, I was actually 3 blocks. So there would somewhere be a tree of parents that allow me to reconstruct. Likely I don't need it, so I can never store that history, but I could keep that somewhere. That's a fair question. Actually, I think something like this might also be the case for the arborescence algorithm, right? That also works based on doing replacement, right? If we don't care about the set of edges, but only about the weights, we can do it a bit less carefully, but if we need to know which edges we have to keep some track once, as we are doing merges of, okay, which edges are which is, right? There, I think it's easier than here, because it's not like we have to go to the end and then go back to the very beginning and keep modifying. Here it's tricky, but the idea is. Okay, any question about this particular problem, and especially about the pattern, like if it prompts you any general question? One more thing regarding the implementation of this one, which would also be a very common trick, which I guess you use often, is to use like a special guarding values or sentinel values, right? Typically, when you have problems on an array, you could add things to the beginning or to the end that you need to make everything simpler, right? For this version of the linked list code, and I guess likely for the set version too, so that you don't have to worry about begin and end being exceptional iterators that you cannot dereference. It is quite convenient to add a few extra values at the beginning and the end. And since you want them to be very bad, so they are never ever selected, you should put huge values there for this problem, infinite, very large numbers. If you do, they will never be selected actually as elements, and so you can run your algorithm and you will never have the current minimum in a border, and you don't even have to handle those situations. And for the linked list version especially, you never get to the situation where something like left of left does not exist with your need. You have to do a pointer correction. Like left of left, right now becomes the current left, right, so on. You want to avoid all of those ifs, so it's nice to add two of them. Adding ones might not be enough here, and people get paranoid and add 10 ones, just in it actually won't impact the performance in a significant way. But 2 is the magic number. 1 might not be enough because even though you will not choose this one, you might choose its neighbor, so it might get merged, right? And now you are very close to the edge, basically, right? So it's no longer the case that you have that extra margin, right? Like one of these might get merged, right? Then once it's merged, it creates an infinite, and so it will not be selected again. But you will have to merge something like this. So if when you do the merge, you want to not be at the border so that you can look at the previous one explicitly, it is convenient to have one more.
Never do the merge because it doesn't. Because that's the.
You might merge this one. This one might be the minimum at any point. And now it has infinity, so it will be merged into a very bad element. But it is convenient for the code to the code being always the same. I want to avoid even the left and right.
Yeah, I'm saying because I put only one and
and you don't check.
Yeah. Because when
okay, this merge, right, this is what I mean. If your merging code that has no problem with there being nothing on the left, then everything is still. But if this might bother you, you might want one more so that when you do the merge, you can delete, and look at the previous of the previous, and there still was something, right? It depends on the details of it.
I only consider log the borders when it's a candidate. When I'm going to use it. I mean, I'm not going to use it because there's like I only see the borders when I need to merge them with their borders, and I won't ever merge that because.
You mean this one or this one?
No.
The second one.
No.
Like this one, you would never need to look because you will definitely never merge this.
The log you draw.
Yes.
That I won't ever see its borders.
Like this, so that you will never look.
Yeah.
Okay. Yes, my code needs to look at this because mainly because of the linked list.
Yeah.
But I don't think you need more than that. But this is a general principle. Like it's good to notice that. I mean, originally I was gonna put more and more ifs. The main message here is that most often than not, you can avoid those ifs by just adding more sentinel values so that if the border is the problematic part, then add more border to the pizza, and then everything is the in-between part. You have no border to worry about anymore. Okay. And this is also very common in problems regarding rectangular boards where you have to fill things, right? You probably have handled problems like that before. It is very common. Depending on the problem, the corners of the board might be very hard to check. Like many times, it's just a simple range check. But at some situations, it could be more troublesome. If it is, you can expand the board and add extra walls or whatever that means. Sometimes it's not even walls, but free space. For example, it happened actually in one of Andrew's lectures that you wanted to count rectangles or things like that, and you can get confused if you have rectangles on the border. So it's easier to expand a bit, and now you are guaranteed to have like a free region on the border, and that avoids corner cases. They are called corner cases because they are at the cost. It's very literal in this case. Okay. Any other question? Comment? Okay, I think that's it. Now, let's go have lunch and hope you have fun today's.